Welcome to This Explainer. Today, we're going to do something pretty incredible. We are going to treat an everyday desktop computer exactly like a biology dissection lab. Our goal here is to completely demystify that staggering, nanoscopic labyrinth of hardware hidden inside the metal case sitting under your desk.
Here is our roadmap for today's anatomical tour. We'll start with the anatomy of a computer, then look at the brain, our CPU architecture. Next, we'll cover powering and connecting everything, followed by the muscle, which is GPU processing, and finally, we'll wrap up with memory, storage, and peripherals.
All right, part 1, anatomy of a computer. Welcome to the dissection lab.
To start off, we really need to change our perspective. We shouldn't view a disassembled computer as just a magic box, but rather as a meticulously engineered city. There's a great quote that says, "Alone, each of these components doesn't do much at all, but when united, they combine to form a powerful system." It hits the nail on the head. A pile of circuit boards won't write an email for you, but together, this machine is a multidisciplinary marvel of engineering, technology, and art, all working in perfect unison.
Moving on to Part 2, the brain, or CPU architecture.
Let's start right in the middle of the motherboard. The central processing unit connects to the rest of the system via roughly 1,200 distinct landing pads. But what's really fascinating is what happens when you peel back its outer metal cover, the integrated heat spreader. Hidden underneath is this tiny, wildly complex integrated circuit called a die. This is where the actual thinking happens, housing functional sections like the 10 processing cores that execute all your software instructions.
10 billion. That is a massive number. It represents the 8 to 10 billion microscopic transistors crammed into just that single tiny CPU die. We are talking about an almost unfathomable scale of engineering here.
And actually, the crucial point to remember is that these aren't just laid out flat. These nanoscopic transistors, which are literally only a few nanometers wide, form the foundation of a complex three-dimensional highway. They're topped by multiple layers of metal wires and vertical connections we call vias. This multi-layered labyrinth is exactly what allows your computer to execute billions of operations every single second without missing a beat.
Let's jump into Part 3, powering and connecting everything. This is essentially our system's nervous and circulatory systems.
You see, while the CPU connects directly to high-speed stuff like memory and graphics, it can't handle every single connection by itself. It relies entirely on a microchip called the chipset. You can think of the chipset as the motherboard's primary traffic director. It diligently manages the flow of data for your Ethernet, your Wi-Fi, USB devices, storage drives, and even the audio pumping out of your speakers.
Now, to do all this computing, the system needs heavily regulated power. Before electricity even reaches the CPU, the motherboard's voltage regulator module drops the power supply voltage down to an ultra-efficient 1.3 volts. But hey, don't let that low voltage fool you. The CPU still consumes enough total power to light up 16 standard LED bulbs, and naturally, that generates a massive amount of heat.
So how do we handle all that intense heat? Liquid cooling. This specific cooler uses a really fascinating, leak-proof brushless DC motor. It drives a constant 4-step cycle. It pumps liquid to absorb the CPU's heat, sends it through radiator channels, uses fans to blast that heat out into the air, and then returns the cooled liquid right back to the pump. It's basically exactly like the radiator in your car, just miniaturized for a silicon brain.
That brings us to Part 4, the muscle, better known as GPU processing.
If the CPU is the brain, the graphics processing unit is undeniably the heavy lifter. Inside the GPU's die, you will find an astounding 11.8 billion transistors, but they're arranged way differently than in the CPU. They actually form a staggering 3,584 simpler processing cores, which are organized into 28 streaming multiprocessors.
This right here brilliantly illustrates the classic difference between brain and muscle. A CPU might only have 10 cores, sure, but they are incredibly complex. We're talking deep pipelines and branch prediction for complicated sequential operations. A GPU, on the flip side, completely trades that complexity for sheer volume. It has thousands of very simple cores designed strictly to distribute and execute massive amounts of basic arithmetic all at the exact same time.
To really visualize why we need a dedicated GPU for rendering beautiful displays and high-end games, think about this. Say you want to brighten an image made of 16 million pixels. You just need to do simple math. Add the number 20 to every single pixel's color value. Well, a CPU can only do that to 10 pixels at a time.
A GPU? It distributes that task across its thousands of cores and just does it instantly. It is built from the ground up for magnitudes more parallel processing.
Finally, Part 5, Memory, Storage, and Peripherals. Let's look at how the system remembers things and interacts with us. When we talk about memory, it's all about one massive physical and performance trade-off. At the top end, we have DRAM. It is blazing fast, accessing data in mere nanoseconds, but it only holds information temporarily. On the other end of the spectrum, you have solid-state drives and hard disk drives. These give you permanent, cheaper storage for your files, but the catch is they are dramatically slower.
Let's zoom in on the solid-state drive, or SSD. Inside, we find an architectural marvel called 3D NAND. Because it has to permanently store your data, it actually stacks memory arrays 100 to 200 layers tall. It literally builds microscopic skyscrapers of data, using tiny charge traps to hold on to 3 bits of data per cell. So even though accessing it is 3,000 times slower than that temporary DRAM, this vertical 3D stacking means a single tiny microchip can permanently hold entire terabytes of your photos, videos, and games.
Now, compare that to the older hard disk drive. These guys take agonizing milliseconds to access data. Why? Well, because they aren't purely electronic. They actually have to wait for a physical, mechanical read/write head to literally sweep across a magnetic disk that's spinning at thousands of RPMs. It's essentially a microscopic, hyperfast record player inside your computer. Bringing it all the way back out to the macro level to your desk. All of this staggering nanoscopic processing power relies on surprisingly simple physical mechanics to register your inputs. That mouse you're holding, it just uses a tiny infrared light and an image sensor to track movement. Your keyboard relies on basic plastic traces. When you press a key down, you are just physically squishing those traces together to complete a simple electrical circuit, which sends a signal straight to that multi-billion transistor brain.
We've just seen how incredibly complex, unified, and intricately designed this physical ecosystem is today. But, seeing 10 billion transistors fit into the palm of your hand leaves us with a profound question. As we keep shrinking these silicon highways down to just a few atoms across, how much smaller and more powerful can the anatomy of a computer actually get before we simply run out of room and hit the absolute limits of physics? It's definitely something to think about the next time you boot up. Thanks for joining me on this explainer, and keep your curiosity switched on.